So the different measuring devices. The first one to talk about is what's called scintillation. Scintillation is when a material emits light when it's exposed to a radiation source. You guys have heard about scintillation when we talked about digital radiography, and we talked about the indirect conversion DR radiography. It was a ways back, but in any case, remember the word scintillation, and scintillation means the immediate emission of light when exposed to a source of radiation. So a material that can emit light when exposed to a source of radiation. Most use a hermetically sealed, so a sealed up, isolated crystal made of sodium iodide or cesium iodide. Importantly, these materials emit light when they are exposed to X-rays, when they're exposed to particulate radiation. So you take that detector that can emit light when exposed to radiation, and as you may guess, the more light, the more radiation, or the higher the energy of the radiation, the more light will be emitted. So the amount of light emitted from a scintillation detector is proportional to the amount, the intensity, and the energy of the radiation. Higher energy equals more light, more intensity, more radiation equals more light. Okay? More light produced by the detector, scintillation detector. That's all fine and good, but you cannot just take a scintillation detector and have it light up when a radiation source is around and look at it and go, yep, that's how much radiation I'm exposed to because it lit up kind of bright. That just won't work like that. So what you'll need to do is you need to have a scintillation detector that can light up when exposed to a source of radiation, and then you need a device that can take that light and convert it into an electric current. Okay? So for that reason, scintillators are attached to something called a photomultiplier tube. Photo for light, multiplier for making more of it. The light emitted from the scintillator, the light came from the X-ray energy. Okay? So the scintillator emits light when exposed to X-rays. That light strikes something called a photocathode layer. A photocathode is a negatively charged material that when it is struck by light, it will emit electrons. This is something called the photoelectric effect, and Einstein showed that this could happen in 1905. So we've known about this for a lot of years. Einstein actually won his only Nobel Prize for this thing called the photoelectric effect. So you have a material that when it's exposed to a certain energy of light, emits electrons. You got the light because the X-rays struck the fluorescent material. X-rays strike fluorescent material emits visible light. Visible light hits the photocathode emits electrons. Okay, and then now you have the beginnings of an electric current, right? Electrons moving is electricity, right? So you're converting X-ray energy into electric current by this step process of conversion of energy. So you make electric current. The electrons are then accelerated and multiplied by a series of these structures called, I'll show you a picture in a minute, by a series of these structures called diodes that amplifies the electrical pulse. This is a part of the amplification process. So here you go. X-rays come in from the left side. They strike this crystal, which is just represented as the cylinder here. That crystal absorbs the X-ray. So I want to take one big step back because what we're doing is we're converting energy, right? We're taking X-rays and converting it, okay? So I need to give you guys one major principle that this operates on. This operates on the principle of the conservation of energy, okay? Who's heard anything about the conservation of energy before? All right, Francisco, what do you know about conservation of energy? You've heard that there is something called the conservation of energy, right? Okay, remember when I took and I dropped that book to the table and I made the big sound, right? I said, where'd that sound come from? And everyone said, well, the book hit the table, right? What happened?
You had the book somewhere in the air, just kind of holding its place. Then when you dropped it, when it came down, like that speed momentum coming down, when it did impact the table, it was just basically, all that energy that was traveling just kind of smacked the table at once.
So what type of energy did the book have when I was holding it up here?
Kinetic energy.
It wasn't moving yet, right? I was holding it, right? So it had an energy of its position. It was high. It had gravitational potential energy. It was held above the tabletop, right? How did it get there? Well, I lifted it. So we'll stop the story here, right? Because we can take the story all the way back to the beginning of the universe. But I stopped the story with I'm holding the book in the air, so the book has potential energy. It's like standing at the top of a hill and then getting on your skateboard and rolling down the hill, right? At the top of the hill, you have potential energy to roll down that hill, okay? My book was up here. It has potential energy. When I let the book go and it began to fall, it lost position. It came down closer to the table, right? As it loses potential energy, it's gaining kinetic energy. It's speeding up, right? At the point when that book hit the table, it had lost all of its potential and gained the maximum of its kinetic energy, okay? The moment that it struck the table, the kinetic energy, its energy of movement, was converted into vibrations of the table. So kinetic energy of the table, kinetic energy in the air by vibrating the air and making that sound, moving the molecules around in the table just a little bit to heat them up, okay? I basically took potential energy, converted it to kinetic energy, and then converted that kinetic energy into a bunch of other forms of kinetic energy, spreading that energy around the room, right? But importantly, if we were extremely accurate and we were able to detect what was the potential, what was the maximum kinetic, and then what was the energy in the sound, what was the energy deposited into the table, we could get back all of the original energy. All of that energy was conserved. None of it disappeared, okay? So the law of conservation of energy says energy is not created or destroyed. It's not lost, right? When I dropped that book and it hit the table and vibrated everything, that energy didn't go away. It just got converted into many other types of energy, mostly kinetic energy of other things, the air in the room, the vibration of the molecules in the table. There was a conversion, okay? The energy dissipated and spread out, but it's all there somewhere, okay? That's the point of the law of conservation of energy. It says that energy is not lost, okay? An X-ray beam carries energy. In fact, X-rays are a form of what's called potential energy, okay? They move through space, but at a constant velocity with no mass and no charge, and all they carry is the potential to deposit energy into something, okay? So an X-ray photon comes along, and it strikes the fluorescent crystal. It takes all of its potential energy and it dumps it into the atoms in that crystal. Those atoms then convert that potential into several photons of more potential energy. So you're converting X-ray potential energy into those green little wavies of, in this case, visible light, okay? Let's say one X-ray photon comes in and converts all of its energy into these 4 photons of visible light by hitting the atom, okay? Those 4 photons, if you added up all their energy, they would have exactly the amount of energy that the one original photon had. There's a conservation of energy there, okay? No energy was lost. So one X-ray photon comes in, boom, hits the fluorescent crystal. 4, in this case, it's not 4 always, it's never exactly this, but you get the point. The one photon converts to 4 photons of visible light. Those visible light photons now carry potential energy. How much? They carry exactly as much as was absorbed, okay? Now these guys are going to strike this layer called the photocathode, okay? When those photons of light strike the photocathode will absorb those photons, will absorb that potential energy. The atoms will. Those atoms absorb that potential energy, and that potential energy gets deposited into the electrons in the atoms. And here there's a conversion, okay? Potential energy from those 4 photons is now converted into the kinetic energy of the electrons that absorbed those photons, okay? So you took potential energy, photons, and you converted it into electrons moving fast. The photons are gone now. They got absorbed into the electrons, and now the electrons are moving, okay? Those electrons are moving because they absorbed potential energy, and it was converted to the kinetic energy of the electrons. So now we have electrons moving. Again, now you have the beginnings of electric current, okay? Electrons moving. Those electrons had kinetic energy all on their own, but importantly, this photocathode has a negative charge to it. It has a current running through it, and it has a negative charge. We know electrons are repelled from like charges, okay? And they're attracted towards positive charges because electrons are negatively charged and opposites attract, like charges repel. Now these structures here called dinodes, these dinodes have the capability of turning on and turning off, charging and uncharging, charging and uncharging. And what they'll do is they'll push and pull that stream of electrons back and forth across the dinodes, speeding them up, increasing their kinetic energy, effectively amplifying their signal, okay? Those dinodes speed up the electrons, and again, the amount of electrons liberated from the photocathode is proportional to the amount of light they absorbed. The amount of light that was emitted from the crystal is proportional to the amount of energy that was absorbed into the crystal, the amount and intensity of the X-ray beam, the intensity and the energy of the X-ray beam. So there's never a loss of energy here. So once these electrons get out the other side, they are proportional. The amount of electric current in this line is proportional to the amount of starting energy, to the intensity and the energy level of the X-rays that struck the fluorescent crystal. So we can infer and calculate from the amount of electric current generated, what was the exposure, right? What was the overall exposure? We can calculate the exposure based on the amount of electric current generated in this device called a photomultiplier tube. And it has 2 parts, as we said, the fluorescent crystal and then the photomultiplier tube that has a cathode end that liberates electrons when struck by visible light. The electrons are sped up through the tube and then fed into an into a line. Okay, that line is then run through an amplifier and then digitized and read out to you on a computer screen in an amount of current. Okay, but importantly, the law of conservation of energy allows us to build devices like this and accurately measure the amount of electricity created and infer from that what was the amount and energy of the original X-ray beam that struck the fluorescent crystal. Okay? Because the law of conservation of energy just says that energy is conserved. So we're just converting. We're converting one type of energy into another, and then amplifying that. That's the photocathode. This is one of the main principles behind detection devices that are used to measure X-ray intensity. Okay, if we wanted to measure counts per second, radioactivity, like particulate radiation, we're going to use another device that I'll talk more about later. Okay, but this is like the primary way that X-rays can be detected. So any X-ray detector device will use this. The state inspectors, when they come through, they measure the X-ray beam intensity. They use a device just like this. Okay, it's usually like a briefcase-sized thing, but they use a device just like this.
So this scintillation detector is not in the X-ray tube?
No.
Okay.
This is a measurement device that's used by inspectors, radiation physicists, people who come and calibrate equipment. They're going to use this to make measurements. Yeah. So yeah, your X-ray tubes can't make any measurements. Okay. Your X-ray tubes just make X-rays, right? Based on your settings that you create. The only way to take a measurement is to bring a device in like this, set it on the table, make an exposure, and measure the intensity. Yep. All right, that's one type, again, used by inspectors, used by physicists, used by anyone who wants to measure the intensity and energy of the radiation from your X-ray tube at different points. I had a inspector come into the office that I no longer work for, but somehow still get to go help with their X-ray room. So I had to go and hang out there and deal with the state inspector. And he took his detector, this guy, scintillation detector, and he used it under the X-ray tube to measure the beam. And then he took it outside of the room, and we made exposures in the room, and he measured if there was any radiation leaking through, coming through the lead walls and on all sides of the room to make sure that, because on one side of the room we had one side we have an area where we do our drug screens. We have like a partially occupied area. And we have another area on the other side of the wall is where our back office is. So we've got like our workers' comp coordinator sits directly on the other side of that wall, right? So we want to make sure that she's not getting exposed unnecessarily. The people at our drug screen area are not getting exposed unnecessarily. And so he's going to make measurements like that to make sure our structural shielding is up to code where it needs to be.
So he's doing those exposures.
Mm-hmm.
Say if he's in the room parallel to where you're at, you have to make an exposure when he tells you to, so that the machine can pick up to see if there's any radiation.
Yeah, because he has to like reset it each time. So he resets it. We make the exposure. He of course stands behind the barrier with us. And then when he goes outside of the room, he just goes outside of the room, and we wait a couple seconds and make the exposure. And he's able to measure it at each different point in the room.
So
Yeah.
then it's multiple exposures.
Multiple exposures, and he's measuring from different areas. Yeah. Yep. So they'll use something very much like this.